Hi, this is Doug Cothe from Oak Ridge National Lab. I'm the director of the Exascale Computing Project, and it's my pleasure to give an update on ECP, as we call it. It's been a while since we've talked to the HPC user forum folks. So I want to thank Earl and Steve and all the folks there for giving us the opportunity to share where we've been and what we've been up to in the past year or so. Again, as a reminder, ECP is part of a broader Department of Energy Exascale Computing Initiative, or ECI. Basically consists of three pieces. This project, which I'm going to give an update on, as well as system procurement projects and facilities, in particular Frontier at Oak Ridge, Aurora at Argonne, and El Capitan at Lawrence Livermore, as well as selected program office application development efforts. I'm going to talk today in particular about ECP. So as a reminder, our DOE HPC roadmap to exascale systems is shown here, and a lot's happened in the past year or so. We do see that we know a fair amount about the exascale systems that are really impending. They're really coming very soon. The Frontier system at Oak Ridge, AMD-based hardware, in particular GPUs. The Aurora system with Intel. Perlmutter system is a very nice system being put together as we speak at Lawrence Berkeley as NVIDIA-based GPUs, and El Capitan at Livermore also has AMD-based GPUs. So really to date, although as of about a year ago, a lot of our efforts and experience have really been on NVIDIA GPUs, and so we've been focused on making sure we can still run well on those GPUs, but being able to perform in a performant way on the AMD and Intel GPUs, and we've had some good experiences there to date in the last year or so. The specs of the Aurora and Frontier exascale systems are here. This is a slide that you can find online, actually, that was posted last November. And so the details of these impressive systems are really becoming firm, and they're real. In particular, on the far right, you'll see the NERSC pre-exascale system, Perlmutter, which is being delivered as we speak. Basically has NVIDIA-based A100 GPUs. The old OLCF exascale system known as Frontier will be delivered in a matter of months, okay? And then next year, the Aurora system. And so they're really quite impressive. We're excited about the hardware. We've had good experiences to date on early versions of this hardware, and so I think one of the key messages I want to deliver is that the work we've done to make sure we perform well and get enhanced science out of the NVIDIA GPUs is really paying off in terms of the preparation for the Intel and AMD GPUs as well. As a reminder, the ECP's technical focus areas are really three: application development, or AD, software technology, or ST, and hardware integration, or HI. In reflecting back on the Exascale Computing Project, which is a formal Department of Energy Order 413.3b project, which means we follow a fairly standard set of formal project management processes, this project has been formally ongoing since July of 2016. So we really are approaching our 5th year anniversary for a nominally a 7-year project. So our teams, which consist of about 80 R&D teams, research and development teams, have been executing for almost 5 years. And so we're beginning to see the fruits of our labor and beginning to see some great results. So I'll tell you a little bit about what's happened in these three areas, in particular focusing on AD and to some extent ST. So as a reminder, our application portfolio, and apologies here because the big green box here is covering up our portfolio, but I'll speak to it a little bit later, consists of 24 application projects and 6 co-design projects. Each application project typically has multiple distinct codes. In fact, 78 separate codes are included in this portfolio. Over 10 million lines of code supporting large user communities and covering a broad range of DOE mission-centric science and engineering domains. When we started, mostly we're all MPI or MPI plus OpenMP on CPUs. And so each project had its own very specific development plan that includes physical model development, applied mathematics, computer science, software engineering, really targeting new and better science, more enhanced science, more predictability, as well as improved performance. So really the current status, as I noted, they all have their unique development plans. They really made tremendous progress on the Summit system here at Oak Ridge. The performance has far exceeded expectations, and most of our applications are really integrated and adopted certain software abstraction layers or co-design motifs, and I'll speak a little bit more about what's going on there. And about half these applications are really on the hook to show formally more than 50x increase in science work rate performance. And so far, based on the Summit experiences, we're very much on track to deliver on those objectives. So the applications in general have been following a variety of programming models, in particular programming on the metal as we speak, as we refer to it, either with CUDA for GPUs for NVIDIA, or HIP AMD, or SYCL Intel. Refactoring the code to work well with the GPU is a majority of the effort. An increasing number are beginning to use C++ abstraction layers, in particular the Raja effort out of Lawrence Livermore and Cocos effort out of Sandia is really being more widely adopted. Luke Pragma models with OpenMP and OpenACC are important in many code bases, especially those that are Fortran based. We're beginning to get experiences with OpenMP target offload and working hard to drive that effort to be able to give us the performance portability that we need. And what's been kind of interesting and to some extent surprising, our co-design motif layers or middleware layers have to some extent been adopted in their entirety as a portability layer as well by many applications, which has been really a nice development to see move forward. We've done a lot of work the last year in really diving deep and understanding our what I'll call our dependencies, both at a high level, what languages are being used, what GPU programming models are being used. And so there has been significant movement, since the beginning of the project, and most of these teams got started in the fall of 2016 in terms of adopting more aggressive adoption of C++ and abstraction layers and libraries. And you can see the distribution here, where the majority are C or C++. A lot use Python, either as glue or exclusively. In terms of Luke Pragma models versus abstraction versus native versus co-design, it's kind of an even mix. I think that's not surprising, given the breadth and depth of the applications that we're supporting. And again, as we back off and say, what are the trends in internode programming? In other words, between nodes, and MPI continues to be the workhorse there. The systems relative to Titan at Oak Ridge had 20,000 nodes. We're talking, thousands of nodes, and so the scaling out challenge is not as daunting and onerous as it used to be. But we are supporting improvements in MPI standard and MPI implementations, being able to support the hybrid programming, making sure we can do high bandwidth, low latency collectives, just being resilient and robust. GPU to GPU communication between nodes is very important. And PGAS models, I think, are becoming more and more widely used. So there's still work to be done. It is MPI, but MPI continues to evolve, and certainly ECP is supporting that effort. Not surprisingly, intranode or within node, we're really focused long and hard on trying to exploit the power of the GPUs. Whether it's NVIDIA, Intel, or AMD, you see the vendor-supported options there that we are definitely using. As I mentioned before, OpenMP is an important portable standard for us, and we're supporting efforts there as well. And finally, I'll say a little bit more about Cocos and Raja, which has been really uptaken in a lot of applications, and not just at the home institutions, namely Sandia and Lawrence Livermore. Now let's take a little deeper dive into critical dependencies, which is the application really can't run at all or run with its key functionalities without certain software technology products. And you saw at the beginning that ECP is supporting through its SD portfolio 71 unique products that are deployed. We're deploying regularly through the Extreme Scale scientific software stack. But if you look at the left, basically the number in the y-axis here is the number of applications that need these ST products in a critical way. You can see that the programming abstractions really are the long pole in the tent with regard to critical dependencies. But also, not surprisingly, is linear and nonlinear solvers, applied math, from low-level local dense algebra to scalable sparse linear algebra is really key. And in many cases, the solver efforts are the gating technology with regard to scalability, both weak and strong. This is a really exciting plot that, frankly, we probably couldn't have predicted when we started, namely that the performance results to date on Summit have really far exceeded expectations. What you see here are figure of merit improvements or ratios of science work rate at the beginning of ECP circa 2016 on systems like Titan at Oak Ridge and Meyer at Argonne relative to what we've seen in 2020 on Summit. And so the ratios for these applications that are listed, and apologies because there are acronyms here that really point to specific projects, but you can see the 50x bar in science work rate that these applications are on the hook to achieve. They're well on their way. Now, 50x on Summit doesn't mean that they're done. They have to be able to show this on Frontier or Aurora, and probably just as importantly, being able to simulate and with demonstrable evidence the challenge problem that they've signed up to. So in most cases, they actually can't execute the challenge problem on Summit because it won't fit, or it's too memory intensive, et cetera. But early indications are we're really on track for most, if not all, these applications to achieve this performance. So let me give you some exemplars, and this is the one that's quite exciting. Danny Perez at Los Alamos leads a molecular dynamics effort that's focused on metal alloys known as Exalt, and that's really to go after enhanced accuracy, larger length scales, and being able to integrate longer time scales, hence the Exalt acronym. And what's interesting is you see a speed up of almost 300x, which we never would have planned or guessed. And it's not really because the application code base performed so poorly at the beginning. Quite the opposite. It performed well with the LAMPS effort. This is a molecular dynamics application that really farms off thousands of molecular dynamics applications at one time in what's known as a replica dynamics approach. But you can see, there's about 10 steps or 11 steps shown from baseline to the latest version that incrementally have found anywhere from 2 to sometimes 20x speed up by making various changes in the code. It's not just running better on the GPUs, but refactoring, redesigning, going after new algorithms, different applied math approaches, and bringing in computer scientists from NERSC and application performance engineers really shows the importance of these integrated, multidisciplinary, multi-institutional teams having new, fresh looks at the applications. Quite a remarkable achievement by this application. I want to focus on just a few applications. Of the 24 applications, there are 6 that sit within the energy applications portfolio. This is led by Tom Evans at Oak Ridge, and you see the domains here, and this spans a lot of energy space, whether it's wind energy, combustion engines, nuclear energy, fossil fuel combustion, fusion, or accelerator physics. And this is a nice list of the key motifs, and motifs are what we call common patterns of communication and computation. And surprisingly, for most of our applications, just a handful of them really represent the application footprint on the hardware. You see the programming models. Again, it's an eclectic mix of the approaches I mentioned before. And the key integration points. These are the key software technology products that they absolutely need to be present, to be functional, and to run well for them to achieve their performance goals and their science goals. So I'll talk a little bit about this, a few of the applications. The wind energy one is quite interesting because it's a brand new application built essentially from scratch based on the Adaptive Mesh Refinement Co-Design Center in ECP, or AMReX, out of Lawrence, Berkeley. And this is using AMReX for the base CFD for a wind farm. When I say base, it's the flow among the turbines, and then a moving unstructured mesh application known as Nalu wind around each wind turbine. So you're coupling together an Alerian structured mesh CFD application with a moving unstructured mesh application in terms of overset grids. Very complicated. You have to communicate between the two grids. You've got extreme challenges with PDEs and sparse linear algebra. It's using the COCOS programming model in AMReX. And the real challenges there are fast, sparse linear solvers. Great progress being made here. A lot of challenges lie ahead. So this isn't certainly just is not a porting exercise. Excuse me, a porting exercise. It's some fundamental applied math and new code bases being built from the ground up. This is an internal combustion engine effort led by Jackie Chen at Sandia. Again, a new code base here with Pele LM, low Mach number Pele compressible, built on AMReX again. The motifs, of course, are adaptive mesh refinement. Common theme here is sparse iterative linear solvers, lots of local chemistry, and so sundials and for explicit time integration of coupled chemistry models, being able to do implicit solves, spatially stiff chemistry. This code base has been moving from C++ to Fortran, so a lot of challenges here as well. Great progress being made. Another area is nuclear energy, in particular a focus on full core coupled Monte Carlo neutronics with full core CFD, in this case incompressible LES or DNS on turbulence. So the goal is a full core coupled simulation of a small modular reactor. A lot of real challenges here in terms of refactoring, redesigning a Monte Carlo algorithm from particle-based statistics to event-based statistics. Really led to some substantial speed ups. In this case, a more or less total overhaul of the Monte Carlo algorithm in the shift code. There's an OpenMC code that's also doing similar approaches targeting Aurora. And the NEC-RS has really leaned heavily on the SEED Co-Design Center, which is a co-design center out of Lawrence Livermore, focused on high order finite element discretizations on unstructured meshes. So basically challenges here are branch divergence of kernels, because a given Monte Carlo particle may do different things based on where it is and its probabilities. Unstructured mesh, iteration of steady state, again, two codes being coupled together. So the main thing is we're certainly not supporting just straight porting exercises. These are really, in many cases, new applications being built from the ground up. Also say, the last one I want to touch is chemical looping reactors. This is again I'll call it a brand new application based on the legacy code known as MPICH, which has really delivered a lot of important answers and insights and solutions for the NETL laboratory in the area of fossil energy. But in this case now we're going to take the multi-phase flow algorithms and a somewhat older algorithmic implementation and building a new code base on top of AMReX. Now we're going to use patch-based adaptive mesh refinement. We're going to bring in embedded boundaries, and we're going to bring in particles for the discrete element model, and we're going to model a fluidized bed with gas flowing up through a fluidized bed consists of particles. So we're going to track particles with the DEM algorithm on GPUs. We're going to need embedded boundaries to model the complex geometry, and we want to do lots of layers of refinement. This app also is built on AMReX, and so what we're seeing is an interesting theme here, where these co-design motifs are really being whole frameworks for the applications, and not just for models and algorithms, but for porting efficiently to the GPU-based system. So it's a nice lead into our co-design portfolio. This is led by Tim Gurman at Los Alamos, and you can see that we have 6 co-design centers and a proxy app effort here. And I'll give a few examples of the co-design centers and how pleased we are with how they're going. Again, the adaptive mesh refinement at Exascale or AMReX, this is led by John Bell at Lawrence Berkeley. And for the ECP kind of first mover applications, it's now a critical component for 6 of our applications, and I think a number of applications outside of a formal ECP scope. Its design is very typical and very typical of our co-design centers and a lot of our abstraction layers, which is the application sees an interface to, an adaptive mesh refinement capability or a particle pusher or whatever through AMReX, but underneath are abstractions for MPI, OpenMP, OpenACC, and then below that, programming more on the metal with CUDA HIP and DPC++ for Intel. So a lot of the complexity is for the most part hidden from the application, so they can focus on the physics and the models and the algorithms there for those models, and then defer the complications of porting performant portability to the abstraction to the co-design center. Another very successful effort is the Center for Efficient Exascale Discretizations, or SEED. You see it here, led by Zanio Kolev at Lawrence Livermore. It has a very similar design, as you can see in the top right, where the application code base is seeing a libc, and underneath are backends for the various hardware. So this design is yet not surprising, but it is in fact really working well in terms of being able to allow applications to focus on what they're good at and really defer the complexities of the hardware underneath the cover, so to speak, of a set of motifs to these co-design centers. A third one is particles. Particles are us. Most application codes use a discrete particle model for a lot of their physics, and you can see here. This is an example out of the COPA Co-Design Center. There's a particle pushing library known as Cabana that pushes particles, does particle kinematics or particle mapping to grids, or grid to particles. And you see several applications, in particular the plasma particle and cell effort, XGC, for our fusion application, heavily relies on the particle pushing capability of Cabana. And you can also see something interesting too, which is here's a co-design motif that has also used Cocos as an abstraction layer. And so what we didn't anticipate, and in retrospect probably should have, is the interchanging use and integration of various ST components that are being used to build a larger component that the application sees. Cabana in particular was integrated into an XGC plasma particle and cell code out of Princeton for gyrokinetics in the core of a tokamak, and the replacing of the Fortran based particle pusher with Cabana, C++ based Cabana particle pusher, not only led to being able to port onto Summit, but even better performance for a large code like this, allowed portability and better performance. And so that particle pushing has now evolved from the ions to the electrons, and will begin to move its way through other parts of the code. So we're really pleased. It's not easy to integrate particles into a big code like this. Really pleased with how this has been going. So the ACP teams have been focused the last 9 months or so on getting on early hardware, so early versions of Intel and AMD GPUs. And to date, we've been very pleased with the results, meaning that the efforts we've made in redesigning, refactoring, and repurposing codes and algorithms for the NVIDIA GPUs have paid off. In a lot of the conceptual heavy lifting for the NVIDIA GPUs has paid off directly for experiences here. And so we can't claim success, but evidence is looking good. We've recently done some deep dive reviews. It was last fall in December, actually, on how are our apps doing. And the result of Andrew Siegel, who leads our application effort, is a application assessment report that you can find online. The themes we're seeing year to year are basically changing. And not surprisingly, we're beginning to see that we're beginning to figure out how to use and exploit mixed precision more. So we're focusing more there. Strong scaling is still a challenge, especially for our iterative linear solvers. Being able to use optimized math libraries, we think, is something we need to focus more on. OpenMP is evolving. We still need to do more work on target offload. Being able to use virtual memory, unified virtual memory, in a more effective way also. So you can see the themes that emerge there And so we do track these themes, and they change from year to year. What do these themes mean? Well, we focus more on these efforts with our resources and our efforts to really target these themes. I'll conclude with a few comments about our ST portfolio. And this is led by Mike Aru at Sandia and Lois Kerr from McGinnis at Argonne. You see the 6 areas here. Not surprisingly, you have programming models, dev tools, math labs, data viz, and a software ecosystem. And also NNSA has its own subset here that it focuses on. So this is a great effort that's been ongoing, and 2 really nice efforts. I mentioned Kokos and Raja that came originally out of Sandia and Lawrence Livermore, but really have multiple labs and universities involved in evolving these capabilities. So it's really been a great development. So Kokos, ECP is heavily investing in Kokos, core capabilities, certain tools, and kernels that allow more easy interface with math libraries. It's a multi-lab, multi-institutional effort. It's begun to be explored more internationally, and is finding its way into a number of application and ST products. Encourage you to go listen to the lectures you can see online there. Christian Trott at Sandia is doing a great job in leading this effort. So we're certainly committed to making sure that Kokos is there, and we're pleased that our HPC colleagues and vendor partners are also very committed to making sure that Kokos is there for the DOE portfolio. Similarly for Raja, we're seeing, originally started at Livermore, we're seeing an uptake in a number of codes for Raja. Quite pleased with this effort, and seeing some substantial speed ups for sort of GPU nodes at Sierra and Livermore versus their capacity systems, in particular the SW4 code. You can see a 20x speed up, the GeoSX code a 14x speed up. So it's not just porting and sort of deferring the complexity to others, but also getting that performance. And it's really, I'd be remiss to not mention that MPI just isn't there, magically works. It continues to need to be evolved. The MPICH effort out of Argonne is very important to ECP. We're certainly investing heavily there. Ongoing activities, we're actively involved in the forum. There are ECP application specific issues, making sure that the GPU to GPU communication is there in an efficient way. It is the primary implementation on Aurora, Frontier, and El Capitan. So you can see it's really an ecosystem, and so we're playing a role there. And I'd be remiss not to call out its importance. So with all of our software technology effort, we now have targeted towards 71 products. You can see the legend here in terms of the various functionalities. We're packaging these things, these products up into a handful, half dozen or so SDKs, and putting releases out at e4s.io it was every 6-month basis, and now it's looking like quarterly. We're also beginning to support and integrate AI machine learning frameworks such as TensorFlow, PyTorch, and Horovod, and support a number of different containers. And we're going to be more and more aggressive in what we do with E4S in the future. So what we've done in ECP is we have not moved away from the single open source one product deployment, but by packaging into SDKs and multiple SDKs into E4S, we're really allowing it to be really lowering the barrier of entry for a lot of applications and other ST products, because we're pushing them out aggressively on their facilities. Something potentially as simple as saying module load SDK or module load this product, and things are going to be there. So we're really committed to making sure E4S is there now, but also in the future. And so it's really emerged as a top level component. We're interacting certainly among ourselves, but with all of our 8 colleagues in the HPC community to make sure that E4S will have a long-lived lifetime post ECP, and we're quite optimistic there. Mike Carew and his folks also do a deep dive review of each ST product, and every year, in fact, every 6 months, they release a capability assessment report. So you can see there's a link there for the latest. I encourage you to bookmark exascaleproject.org and look for updates where we put these comprehensive reports. These reports are really a tour de force of what we're doing, a good snapshot of status, but also challenges, issues, and plans moving forward. So in terms of ECP, we believe we are on track for delivering on our objectives. I would say that in the year to come, it's really important for us. It's kind of the penultimate year when the rubber meets the road and we get access to Frontier and Aurora and begin to turn out the results that we expect to see come. You can see in the application development, software technology, and hardware and integration, we're pleased with our product. I mean, with our progress. Not that the next year or so isn't going to be challenging, but we think we're up to the challenge and really ready to roll here after multiple years of preparations. I'll conclude by the question I was given: what have some of the biggest challenges been to prepare for Exascale systems? I think it's really understanding the breadth and depth of programming models and approaches that we needed to take for accelerated node architecture, which I believe are here to stay. I think in terms of the accelerated node architectures, it was really not, the software challenge is not a porting exercise. It's not a software engineering exercise in total. You have to rethink the algorithms, rethink your data structures, and that conceptualization, I think, is every bit, if not more challenging than implementation. And I think, too, the challenges of designing motifs or extraction layers have been there, and they're really paying off. And so I think we're on a good track. Not that challenges don't remain, but it does require some deep thought in terms of how to redesign algorithms and software and data structures to deliver on your objectives. So that said, I'm out of time. I want to thank everybody for your time and attention, and I'd be happy to answer any questions in any of the remaining time. Thanks.